there, 1100. Let's knock this out real quick. You're doing the latent heat of fusion for water. And your lab manual is just 1 page long. It gives you no instruction on procedure or analysis for that matter. Basically what you're supposed to figure it out yourself. Read your lab manual. You'll see what I'm talking about. It's your time to shine. So what that means for me, I just mechanically go through the motions. Of course, I'm going to be saying some stuff though, but that's just for the benefit of you not missing out on like actually handling this stuff on your own. For instance, describing how this is constructed, things that you would need, things that you'll need to know to help you do your analysis. So 10 minutes, let's get started. Okay, here we go. Our calorimeter, which has this inner compartment. This is going to be, or assumed to be, thermally isolated from the rest of this calorimeter. It sits on this little ring. So this isn't in direct contact with this outer shell. And we have a lid. There is this peculiar looking straw, and that's so that I could mix the ice in the water so that this process happens as quickly as possible. And of course, that's just so that we could eliminate the effects that our environment has on the temperature of that water and ice. Our thermometer, it is suspended so that only a portion of it is submerged in the liquid. And that's just because the thermometer was calibrated in such a way that you want it just submerged to this level there. This aluminum canister, per the manufacturer, has a specific heat of 0.22. That would be 0.22 grams per calorie degree Celsius. So let me write down this mass. It is 48.14 grams. That's the mass of our inner container, which we should incorporate, excuse me for a second, which we should incorporate into our equations, of course, because we can't neglect the container that the water is actually in. In other words, when I pour water in here, which I'll do now, I have to hold it by the top. Otherwise, well, I wouldn't be able to hold it from the bottom because it is extremely hot. It is part of our system. Now, let me place it here without scalding myself. There we go. Now, how much water is in here? Sorry about that. That is hot. Okay. Container with water is 231.38 grams. Okay. Figure out what the temperature is. Actually, I'd rather it sit in there for a little bit prior to immediately doing our experiment, and that is because I want to ensure that that outer container is the same temperature as our water. And right now I'm getting a reading of 74 degrees Celsius. 74. Now, let's determine the mass of the ice that we're going to place in there. So this container is 90.18 grams. I'm drying off my ice with my shirt. I don't want water. I just want ice. 114.02 grams is the mass of the container plus ice. You know what? What I should have done is place that lid on. And the reason being is I want this to reach thermal equilibrium with the water. I mean, at this point, we're introducing air anyway. Under normal circumstances, I would incorporate this straw into our equations, but I don't know what the specific heat of that straw is. I mean, we could, that would be a nightmare. I wouldn't want to research to see what type of plastic straws are made of, how long would that take? And then on top of that, you got to find somewhere where that type of plastic is reported with a certain specific heat. I don't know, maybe it would be relatively easy. Maybe plastic in general has the same specific heat. Nah, I bet it doesn't. There's too many varieties. Okay, so we're at 73. So it dropped 1 degree. 73, that is our initial temperature. Let me put this ice in. I'm gonna weigh it one more time. 112.62. It melted a bit. 112.62. It's melted. Take a little peek. We are at 57 degrees. 57. So I weighed the ice again, and that's because, yeah, some of it melted. It is pretty hot in here. So our container plus ice had a mass of 112.62, not 114.02. In other words, like a little more than 1 gram of ice had melted. So that is it. We are going to determine the latent heat of fusion, and let's see how well this guy works. I'm almost tempted to incorporate this thermometer into our equations, but the whole thing doesn't get as hot as just the tip. So the heat transfer is just in a little tiny portion. That's like 1/8 of the mass of that thermometer. The mass of the thermometer is something like 25 grams. So I don't think that we are going to be making much of a correction if we incorporated the tiny portion of the thermometer that was in the water. Actually, the mass is only 16 grams, so 1/4 of that is 4 grams. Leave it out. Okay, so that's it. Good luck on your results.